In the stillness of the cosmos, silence reigns absolute. No wind stirs, no sound travels. It is a darkness so complete that even the concept of emptiness feels inadequate. Against this infinite backdrop, stars ignite like scattered embers, each one a roaring furnace, each one a titan of energy. They burn for billions of years, weaving the elements of worlds, and when their lives end, they collapse with cataclysmic fury. Supernova flare, brighter than entire galaxies. Gamma-ray bursts shoot across space with the power to sterilize planets. These are the explosions that sculpt the universe, rewriting the fabric of existence itself. And yet, even they are not the ultimate expressions of power. For beyond them, lurking in the shadows of collapsed giants, lies something greater, darker, and infinitely more dangerous. The black hole. It is not an object in the traditional sense, but a rupture in the order of reality. Where it exists, matter falls, light bends, and time itself begins to unravel. What was once a star becomes an abyss without surface, without bottom, without escape. The boundary that encircles at the event horizon marks the end of the visible universe for anything that crosses. Beyond that line, no signal, no memory, no final cry can ever return. Here lies the most powerful object known to science, a gravity well so absolute that it defies imagination. The human mind can sketch equations, build simulations, capture shadows of its presence, but never truly peer inside. To look into a black hole is to confront the collapse of every law we know. Space becomes warped beyond measure. Time slows and stretches, and the very foundations of physics begin to fracture. What happens inside? Is there a singular point of infinite density, a place where all the mass of a star is crushed into nothingness? Or does another reality await, hidden from view new universes? Long before science placed numbers on the heavens, ancient eyes turned upward and saw mystery in the night. Constellations were drawn, myths were told, and the sky became a canvas of gods and monsters. Yet even then, the darkness between the stars held a weight of its own. Patches of sky where light seemed absent stirred unease. Civilizations spoke of voids, of places where creation had not yet touched, but none could conceive of a star so heavy, so collapsed, that even light itself would never escape. The black hole remained a secret, hidden in the mathematics of a future still centuries away. That future began to take shape in the early 20th century. In 1915, Albert Einstein unveiled his theory of general relativity, a revolution in human understanding of gravity. No longer was it a simple pull between masses. Gravity became geometry itself, the bending of space-time by the presence of matter. A star, a planet, even a person, all of them left indentations on this invisible fabric. The deeper the indentation, the stronger the pull. Einstein's equations described how the cosmos truly worked, and in doing so, opened the door to the unimaginable. It was Carl Schweitzer, serving on the Eastern Front during the First World War, who first carried Einstein's theory into the abyss. He solved the equations exactly, producing a description of space-time around a perfectly spherical, massive object. Buried in his mathematics was something startling. At a certain radius, light could not escape. Beyond that invisible boundary, every path curved inward. Today, we call it the event horizon. Even Einstein himself recoiled from this implication. The idea of matter collapsing without end, of a singularity where density became infinite, seemed too extreme to be real. He believed nature had limits, that it would not allow such monsters to exist. Many physicists agreed. The singularity was considered a mathematical trick, not a physical reality. In the 1930s, as astronomers studied the lives and deaths of massive stars, the picture grew darker. Subramanian Chandrasekhar showed that above a certain mass, a dying star could not resist its own gravity. No pressure, no force could stop the collapse. It was Arthur Eddington, a leading astronomer of the age, who dismissed the idea, insisting that such an outcome was absurd. To many, the notion that a star could collapse into an infinite abyss was unacceptable. For a time, physicists avoided the name. They spoke, instead of collapsed stars, frozen stars, or simply theoretical curiosities. The term black hole itself would not emerge until the 1960s, when John Wheeler gave the abyss a name that captured its essence. By then, mathematics had grown too insistent to ignore what began as an abstract solution in the equations of general relativity had become a ghost stalking the edges of astronomy. The void that ancient cultures only imagined as myth had reappeared, sharper, colder, and now backed by the logic of science. A new mystery had been born, not a story of gods in the sky, but of nature itself writing riddles into the very structure of space-time, long before black holes were accepted as physical reality. The idea of objects so dense that not even light could escape had surfaced in the imagination of thinkers centuries earlier. In the 18th century, John Mitchell and Pierre Simon Laplace speculated about dark stars, celestial bodies whose gravity might be so strong that their light could never reach distant observers. It was a remarkable intuition, yet entirely abstract, more philosophical musing than observational science. These early contemplations hinted at the darkness to come, a shadow cast across centuries of thought. When Einstein revealed general relativity in 1915, the mathematical framework allowed such objects to exist in principle. Yet even he expressed unease. A singularity, a point of infinite density and zero volume, seemed a step too far. Nature, he believed, must have limits. The notion that a star could collapse entirely, leaving behind a void where the very rules of physics failed, provoked discomfort among the brightest minds of the era. The unease grew in the 1930s with Subrahmanyan Chandrasekhar's work on stellar collapse, calculating the maximum mass that a white dwarf could support against gravity. He demonstrated that stars exceeding this threshold had no hope of halting their inward fall. Gravity would inevitably win, compressing matter into a state beyond comprehension. Arthur Eddington, one of the era's leading astronomers, vehemently rejected this idea, calling it absurd. For a time, even the suggestion that a star might collapse into nothingness seemed unthinkable. Cultural apprehension mirrored scientific skepticism. Infinite density was not only mathematically troubling, it was philosophically unsettling. How could nature allow a point in which all laws break down, where space and time themselves lose meaning? For decades, the black hole lingered as both a terrifying possibility and an intellectual anomaly, a ghost at the edge of physics. And yet, the concept persisted. Slowly, through rigorous calculation, debate, and gradual accumulation of evidence, the black hole emerged from the realm of speculation. It became something more than a mathematical curiosity. It was an object so extreme, so inconceivably powerful, that it challenged every assumption about the universe. The most powerful objects known to science were no longer the explosions of dying stars, or the fury of Gamma bursts. They were the quiet, invisible, and absolute wells of gravity, waiting silently in the darkness, defying both observation and understanding. This was the point where the modern black hole was born, both terrifying and unbelievable, a threshold of knowledge beyond which humanity could see only shadow. As the mid-20th century unfolded, astronomers trained increasingly sophisticated telescopes on the heavens, seeking compact objects that might betray the presence of extreme gravity. The universe, it seemed, was not only vast but full of enigmas waiting for instruments capable of revealing them. Observations in radio and X-ray wavelengths began to hint at phenomena that defied simple energetic and invisible from ordinary sight. In 1963, the discovery of quasars sent a ripple of astonishment through the scientific community. These point-like objects emitted more light than entire galaxies, yet occupied volumes smaller than our solar system. Their luminosity, constant yet staggering, suggested that a source of unimaginable density and energy lay at their cores. Here, indirectly, the signature of extreme gravity was etched across the cosmos, hinting at the presence of black holes as engines of such luminous fury. Among the first concrete candidates was Cygnus X1, an X-ray binary system identified in the late 1960s. Observations revealed a massive, unseen companion to a visible star, exerting gravitational pull so intense that its very presence distorted the surrounding space. The radiation emitted by the swirling matter falling toward this invisible companion offered the first tangible glimpse of a black hole's existence, transforming a theoretical curiosity into a target of observation. Meanwhile, in the abstract realm of mathematics, Stephen Hawking and Roger Penrose were exploring the inevitability of singularities. Their proofs demonstrated that, under general relativity, collapse into an infinitely dense point was not only possible but unavoidable for certain massive stars. The singularity, once dismissed as a mathematical oddity, now emerged as a fundamental consequence of the laws of the universe, a point where spacetime folds into itself and the familiar rules of physics cease to hold. It was also during this period that the concept of the event horizon, the point of no return, was refined. This boundary demarcated the limits of observability, a line beyond which matter and information could no longer escape. The horizon redefined the very notion of boundaries in space, forcing humanity to acknowledge that some regions of the universe were forever inaccessible, yet no less real. Through these combined observational breakthroughs and mathematical insights, the black hole evolved from a speculative abstraction into a tangible object of study. The invisible became inferable, the theoretical began to influence empirical science, and the most powerful objects in the universe transitioned from shadows in equations to phenomena whose effects could be measured, mapped, and contemplated. Humanity, still distant from the interior of these objects, now had the tools to approach their edges and witness the influence of forces beyond imagination. As observational technology advanced, the cosmos revealed further hints of these invisible titans. Space-based telescopes, freed from the distorting effects of Earth's atmosphere, began detecting high-energy X-rays and gamma rays emanating from regions once thought empty. These emissions, often originating from binary systems where one star fed matter into its unseen companion, painted a picture of violence and compression at scales beyond ordinary comprehension. Matter spiraled inward in accretion disks, heated to millions of degrees, emitting radiation that signaled the immense gravitational pull at work. Each flicker, each pulse, became a fingerprint of an object invisible yet undeniably present. Theoretical models and numerical simulations now walked hand in hand with observation. Astrophysicists could map the behavior of matter near these extreme environments, predicting the intense jets of energy sometimes expelled perpendicular to the disk. These relativistic jets, traveling near the speed of light, extended thousands of light years, their origin a testament to the energy stored in the depths of gravity wells. The universe itself seemed to display a duality, destructive yet ordered, chaotic yet governed by precise mathematical rules. Hawking and Penrose's work added philosophical weight to the growing observational evidence. Singularities were no longer merely the endpoints of dying stars, they represented fundamental thresholds of reality, where our understanding of space, time, and matter reached its limits. If the interior of a black hole contained such extremes, then the boundary between the observable and the unknowable became a stage for contemplating existence itself. The event horizon, once an abstract mathematical surface, now became a physical and conceptual frontier. Crossing it would mean entering a realm where past, present, and future lose their conventional meaning, where the arrow of time may twist and fracture under immense gravitational tension. Meanwhile, astronomers expanded their surveys, discovering supermassive black holes at the centers of galaxies. These colossal objects, millions to billions of times the mass of our Sun, exerted gravitational dominion over millions of stars, orchestrating the motion of entire galaxies. Quasars, now understood to be powered by these central engines, revealed that black holes were not rare curiosities, but fundamental players in the cosmic order. Their influence extended far beyond their immediate vicinity, shaping the formation and EAs. The mid-20th century gave way to the modern era of astronomy. Humanity gained instruments capable of seeing the universe in ways once unimaginable. Radio telescopes, probing the invisible whispers of space, began revealing phenomena that challenged conventional understanding. Later, space-based observatories, lifted beyond the veil of Earth's atmosphere, detected X-rays and gamma rays from regions where stars seemed absent, hinting at the presence of objects of staggering density. Each signal carried the imprint of forces so immense that matter itself bent and twisted under their influence. Evidence soon accumulated for supermassive black holes at the centers of galaxies, colossal engines anchoring the swirl of stars and gas. Observations revealed the motion of stars tracing invisible orbits, jets of energy piercing vast cosmic distances, and radiation so intense it could outshine entire galaxies. These discoveries transformed black holes from theoretical curiosities into dominant players in the architecture of the cosmos, their gravitational power shaping the evolution of galaxies over billions of years. The Event Horizon Telescope, a global network of synchronized radio dishes, achieved a milestone in 2019, the first image of M87*, though only a shadow against the bright swirl of surrounding matter. The image revealed the outline of an event horizon, a boundary where light cannot escape. For the first time, humanity glimpsed the silhouette of the universe's most powerful objects, the dark shape that had until then existed only in mathematics and theory. It was a moment of both triumph and reflection, proof that we could detect the contours of the unimaginable. Yet the heart of the mystery remained inaccessible, hidden behind the horizon. Meanwhile, LIGO, the Laser Interferometer Gravitational Wave Observatory, captured ripples in space-time itself, emitted when black holes collided. These collisions released more energy in mere seconds than all the stars in the observable universe combined, shaking the fabric of reality and confirming that the extremes of gravity could be felt across vast cosmic distances. Each detection, each pulse of gravitational waves, became a new sense with which humanity could perceive these otherwise invisible titans. Through these breakthroughs, black holes evolved from theoretical predictions to observable realities. They were no longer shadows in equations or curiosities in astronomers' logs. They were tangible forces capable of influencing light, matter, and time across incomprehensible scales. Yet, despite this progress, the interior, the singularity at the core, where density becomes infinite and the laws of physics falter, remained beyond reach. Humanity could trace the event horizon, witness the fury of accretion disks, and feel the tremors of colliding giants. But the ultimate secret of what happens inside the most powerful objects in the universe persisted, concealed by the very nature of their overwhelming gravity, even as our instruments improve and simulations grow ever more sophisticated. The black hole remains both an object of study and a mirror for human contemplation, a place where knowledge meets its limits, where mathematics touches mystery, and where the universe challenges the imagination itself. Each observation, each shadow and wave detected, deepens our understanding of cosmic power, yet underscores a humbling truth: some boundaries exist not merely in space, but in the very capacity to know. The breakthroughs of the early 21st century did more than expand astronomy. They redefined what it meant to observe. The cosmos, once revealed through visible light alone, now unfolded across a spectrum of invisible messengers. Gravitational waves, neutrinos, and high-energy photons converged into a new discipline: multi-messenger astronomy. Black holes, once silent, now spoke in many voices, each revealing a different facet of their hidden nature. The observation of Sagittarius A*, the supermassive black hole at the center of our own Milky Way, became a triumph of patience and precision. For decades, astronomers tracked the orbits of stars, whirling around an unseen mass 4 million times heavier than the Sun. Their dance betrayed the presence of an invisible anchor. In 2022, the Event Horizon Telescope unveiled its shadow. Though blurred, the image carried the unmistakable imprint of the same gravitational silhouette first seen in M87*. Humanity had peered not into the abyss of a distant galaxy, but into the heart of its own. Each advance underscored the paradox of proximity and distance. Black holes could not be touched, yet their influence stretched across space and time. When two black holes collided, the resulting gravitational waves rippled outward for billions of years, arriving at Earth as whispers in LIGO's delicate detectors. To catch them required engineering of unprecedented sensitivity: laser beams aligned across kilometers, mirrors isolated from the smallest tremors of Earth. And yet, in those faint distortions of spacetime, astronomers could reconstruct the death spiral of giants long gone, their masses merging into something even more immense. These signals did more than confirm Einstein's predictions. They revealed populations of black holes no one had expected. Some were far larger than stellar theory had anticipated, suggesting entire chapters of cosmic evolution yet to be understood. How had these behemoths formed? Were they the remnants of the first stars, or products of runaway growth in dense stellar clusters? Each detection expanded the mystery rather than closing it. The scale of energy involved defied imagination. In the instant of collision, when two horizons merged into one, energy equivalent to several suns was converted entirely into gravitational waves. No light, no particle, only the raw curvature of space-time itself carried the story across the cosmos. For a brief moment, the universe spoke in a language older than matter. Such discoveries were more than technical milestones. They reoriented humanity's place within the universe. To glimpse the shadow of a black hole, or to feel its collision across the fabric of space-time, was to stand on the boundary of comprehension. It was a reminder that the cosmos holds forces both destructive and creative, and that the same objects once doubted as mathematical curiosities now shape the very structure of galaxies. The chapter of black hole discovery is still being written. With every sharper image, every captured wave, the veil thins, though the heart of the mystery remains intact. No telescope can penetrate beyond the event horizon. No detector can yet reveal what occurs past that point of no return. Humanity can circle the shadow, map its edge, and measure its tremors, but the interior remains a silence the universe is not ready to yield. And so, The story of black holes is both one of progress and restraint. Each new window opened shows us more, yet reminds us of how much remains hidden. They are the darkest objects, and yet, paradoxically, they have become some of the brightest beacons of knowledge, illuminating not themselves, but the limits of human understanding beyond the boundary of a black hole. The narrative enters a realm where observation halts and imagination, tethered to mathematics, must take its place. The event horizon marks a frontier unlike any other in the cosmos, a veil that permits entry but denies return. From the outside, it is a sphere of silence, a region from which no signal escapes. From within, it is the threshold to enigmas that stretch the very fabric of human comprehension. The singularity, predicted by general relativity, rests at the heart of this abyss. It is not a point in space, but a breakdown in the very equations that describe reality. Density rises beyond measure, curvature sharpens without limit, and the clockwork of time itself ceases to function in any way that can be meaningfully defined. It is the ultimate collapse, where the known laws of physics no longer speak. Einstein himself resisted the notion, believing nature would not permit infinities, yet his own theory inexorably led to their existence. If the singularity truly exists, it represents a place where spacetime no longer resembles anything familiar. To approach it would be to move beyond coordinates, beyond measurement, beyond the very scaffolding of reality. The flow of time, so steady in the everyday world, twists into forms alien to intuition. Minutes and centuries lose their distinction. Cause and effect blur in a storm of geometry. But even before the singularity is reached, the paradoxes emerge. In the 1970s, Stephen Hawking revealed that black holes are not entirely black. Through quantum effects at the horizon, they radiate faint energy, now known as Hawking radiation. This led to a dilemma that shook physics at its core, the information paradox. If black holes can evaporate over immense timescales, what happens to the information carried by the matter that fell within? Does it vanish forever, defying the principle that information cannot be destroyed? Or does it remain encoded somehow in the radiation, hidden in patterns too subtle to yet detect? This question is more than academic. It strikes at the foundations of quantum mechanics and relativity, two pillars of modern physics that refuse to fully coexist within the extreme conditions of a black hole. To resolve the paradox is to edge closer to a theory of everything, a unified framework that might reconcile the large with the small, gravity with quantum fields, the smooth geometry of spacetime with the restless fluctuations of particles. Some proposals push the mystery further. The firewall hypothesis suggests that the horizon itself might be a violent frontier, wherein falling matter encounters a wall of destructive energy. If true, this would shatter the long-held belief that crossing the event horizon would feel unremarkable to a falling observer. Others argue for more subtle resolutions, envisioning the horizon as a holographic surface, a cosmic ledger encoding every detail of what has passed through. In this view, the black hole becomes less a void than a vault, its surface storing the secrets of the interior. Each theory is both daring and incomplete, glimpses of a truth that refuses to fully emerge. The black hole thus becomes a paradoxical laboratory, not accessible to experiment in the traditional sense, yet unavoidable in the equations that govern the universe. To study them is to confront the boundaries of knowledge itself. As humanity gazes upon their shadows and listens to the tremors of their collisions, the questions grow sharper. What lies beyond the horizon? Does the singularity truly exist, or does quantum gravity smooth the abyss into something yet unnamed? Is the information of the universe preserved, or does the black hole write its own rules? No final answers exist, only the deepening of mystery. And in that mystery lies a mirror, reflecting the limits of human reason and the enduring drive to see beyond the dark. The black hole is not merely an object of destruction, it is the stage where the universe tests the very logic of its own existence at the edge of understanding. The mystery of the black hole deepens not with silence, but with contradiction. Each attempt to pierce its secrets reveals more layers of paradox. Like a riddle that rewrites itself whenever one approaches an answer, the singularity, the information paradox, the horizon itself, each has become a battleground where the most advanced theories of physics collide, often leaving more uncertainty than clarity. To many, the singularity is not a final destination, but a signal of incompleteness. General relativity, flawless in describing stars, galaxies, and the vast architecture of the cosmos, falters in this crucible of gravity. It is as though nature is whispering that relativity is but a chapter of a greater story. Quantum mechanics, with its language of probabilities and uncertainty, must also enter the equation, yet it resists union with gravity. Somewhere within the black hole lies the point where these two great frameworks must reconcile or collapse into contradiction. Here emerges the tantalizing possibility of quantum gravity, a theory still out of reach, yet glimpsed in speculative architectures like string theory and loop quantum gravity. Some suggest that singularities may never form at all, that quantum effects prevent infinite collapse, leaving behind a core of extreme but finite density. In this vision, the singularity dissolves, replaced by a quantum remnant where spacetime is granular, woven from loops or strings too small to imagine. The information paradox sharpens the puzzle further. If matter disappears into a black hole, carrying with it the patterns of the universe, how can the laws of physics remain intact? Hawking's early calculations implied a grim conclusion: information is destroyed, cast into nothingness. But such destruction violates the bedrock of quantum theory, which demands that information be preserved, no matter how scrambled. This tension has ignited decades of debate, inspiring theories that stretch from the holographic principle to the concept of black hole complementarity. The holographic idea suggests that the universe itself may function like a projection, where the three-dimensional world is encoded on two-dimensional surfaces. A black hole, in this framework, becomes a cosmic hologram, its surface etched with the information of everything it consumes. What appears lost within may instead be preserved at the horizon, written in patterns still beyond human decoding. If true, the black hole is not a tomb, but a library, its shelves hidden in the curvature of space. The firewall hypothesis deepens the tension by challenging the notion of a gentle crossing. For decades, relativity suggested that an observer falling past the event horizon would notice nothing extraordinary, at least until reaching the singularity. The firewall disrupts this narrative, replacing calm passage with catastrophic annihilation. In this version of reality, the horizon itself becomes an inferno of quantum energy, burning away anything that dares to cross. If this is true, it would mean that the event horizon is not the silent boundary once imagined, but a violent edge of reality. And yet, not all theories embrace destruction. Some propose that black holes are portals, linking distant regions of spacetime through wormholes, or even opening pathways to other universes. Though highly speculative, these ideas are not merely flights of imagination. They emerge naturally from the mathematics of relativity, whispering that the abyss may conceal connections as profound as creation itself. What unites all these perspectives is the sense that the black hole is not simply an endpoint. It is a paradoxical stage where the universe demands new physics, where the laws humanity has trusted reveal their limitations. To study it is to be reminded that knowledge, however vast, is always incomplete. The black hole resists simplification. insisting instead on mystery. In this deepening enigma, humanity confronts more than equations. It confronts a reflection of itself, the desire to know, colliding with the recognition that some truths may remain veiled. Yet even this veil has power, for it draws curiosity forward, compelling new generations of thinkers to challenge the limits of imagination. The black hole remains both a threat and promise, the most destructive force in the universe, and at the same time, perhaps the key to its deepest unity. Beyond the horizon lies not only darkness, but the possibility of revelation. At the frontier of knowledge, black holes stand like sentinels, guarding secrets that lie beyond the reach of present understanding. They expose the limits of the two great pillars of modern physics, general relativity and quantum mechanics. Each is astonishing in its domain, relativity governing the curvature of galaxies and the dance of planets, quantum mechanics shaping the restless lives of atoms and particles. Yet, within the crushing heart of a black hole, these two systems clash, refusing to coexist. The abyss demands a new synthesis, a theory not yet born. General relativity describes the black hole as the ultimate triumph of gravity, space-time collapsing into a singularity where curvature becomes infinite. But quantum mechanics cannot accept infinities. In its world, reality is discrete, probabilistic, never boundless. When applied to black holes, quantum rules imply that collapse should halt before reaching absolute density, reshaping the story written by relativity. The singularity becomes a puzzle piece that does not fit, a warning that something deeper must underlie both frameworks. This search for reconciliation leads to the dream of quantum gravity. It is a theory glimpsed but not yet secured, pursued by the architectures of string theory and loop quantum gravity. String theory imagines the fabric of reality as vibrating strands, smaller than quarks, resonating at scales far beyond detection. Loop quantum gravity envisions spacetime itself as woven from loops, discrete grains of geometry that cannot be divided further. Both suggest that the continuum of spacetime is an illusion at the smallest scales, and that within a black hole, the smooth collapse predicted by relativity would dissolve into a quantum texture. At these unimaginable depths lies the Planck scale, the threshold where the known dissolves into the unknown. Distances of 10^35 meters, times of 10 to 43 seconds, intervals so brief and so small that even thought struggles to grasp them. At this scale, gravity must be quantized, space may be granular, and time itself may not flow as a river, but tick as a sequence of indivisible moments. A black hole interior, in this view, becomes a laboratory of the Planck scale, compressing the cosmos into realms unreachable by any other means. Speculation grows naturally from this foundation, not as fantasy, but as necessity. If one could fall into a black hole, what would the experience be? Relativity whispers of a calm descent, the crossing of the horizon unnoticed. To the outside world, the faller would appear frozen, time stretching infinitely. To the traveler, time would continue, carrying them inward, faster and faster toward the singularity. Yet quantum mechanics complicates this serene vision. Would a firewall blaze at the horizon, erasing them in an instant? Would their information smear across the event horizon, encoded forever in its surface? Or would the descent reveal layers of reality no human has yet conceived? Even wormholes emerge from this tension, not as science fiction, but as legitimate solutions to Einstein's equations. Some interpretations suggest that black holes may not end in singularities at all, but instead connect to distant regions of spacetime. These hypothetical Tunnel-Einstein-Rosen bridges might link galaxies, or even universes. Yet they are unstable, collapsing too quickly for passage, unless exotic matter with negative energy could hold them open. Though no evidence exists, the mathematics offers a glimpse of a cosmos where black holes are not just destroyers, but gateways. At this edge, the line between science and speculation grows thin, but it is a line that must be walked. For to understand black holes is not only to refine existing laws, but to envision those that have yet to be written. They are the proving grounds of the future, the crucibles where human thought is tested against the harshest enigmas of the universe. Beyond the horizon lies not only collapse, but the possibility of unification, single language of nature, that may one day dissolve the fracture between relativity and quantum mechanics. The black hole, then, is not simply a destructive void. It is the stage on which the next revolution in physics may emerge, pressing human reason to its limits and beyond them. At its core lies the ultimate question: what is reality made of when space-time itself falls apart? Until that answer arrives, the black hole will remain the extreme edge of science, where wonder and uncertainty intertwine. At the extreme frontier of knowledge, science meets its sharpest contradiction. General relativity describes the smooth fabric of space-time, bending under the weight of stars and black holes with majestic precision. Quantum mechanics, in contrast, governs the subatomic world, where uncertainty rules and probability defines reality. Both theories have passed every test within their own realms. Yet when brought together at the heart of a black hole, they clash violently. Mathematics refuses harmony, and the universe seems to guard its final secret behind a curtain of incompatibility. Physicists speak of the Planck scale, a threshold where the dimensions of space and time shrank to 10⁻35 meters, far smaller than any instrument could ever probe. At this scale, the very notion of geometry dissolves. Distances blur, time loses continuity, and space-time itself may become a storm of quantum fluctuations. It is here, beneath this veil, that a theory of quantum gravity must reside, a framework capable of merging Einstein's curves with quantum uncertainty. String theory imagines vibrating filaments of energy as the building blocks of all matter and force, while loop quantum gravity envisions space-time itself as a vast web of discrete loops, woven into a cosmic fabric. Both offer glimpses, yet neither provides a complete key. Thought experiments often push this mystery into human terms. Imagine a person falling toward the event horizon. To an outside observer, their descent would appear to slow endlessly, frozen by the time dilation of extreme gravity. But for the falling traveler, time would flow normally, carrying them past the horizon without resistance. What comes after defies prediction. Would they confront a searing firewall of high-energy quanta, as some theories suggest, annihilating them before entry? Or would they glide past the threshold in silence, only to encounter the warped landscape where classical physics dissolves into chaos? Beyond speculation lies another possibility, born from the equations of general relativity. These hypothetical tunnels might link distant regions of the universe, or even different universes entirely. Could the heart of a black hole conceal such a gateway? Mathematics permits the idea, though nature may never allow it to form. If wormholes exist, they would challenge the very idea of a beginning and an end, replacing finality with passage. At this frontier, the line between established science and speculation grows razor-thin. Yet speculation is not folly, it is a necessity. Without daring to imagine, physics cannot progress. Black holes, in their silence, demand this imagination, forcing the human mind to stretch beyond the tested into realms uncharted. Each question they raise draws science closer to its own horizon of understanding, and so, at the extreme edge of science, black holes become not merely cosmic phenomena, but mirrors of human curiosity. They remind us that knowledge, like the universe itself, is unfinished, expanding outward, searching for a language that can hold both the vast and the minute, the continuous and the uncertain. It is here, in the collision of relativity and quantum mechanics, that the next revolution awaits. Hidden in the darkness where science and mystery meet. At the center of every black hole lies the singularity, at least as classical physics describes it. Here, density grows without bound, and space-time curves until its geometry becomes undefined. It is the place where Einstein's equations, so powerful across the cosmos, surrender to infinities they cannot resolve. In this mathematical abyss, distance and time lose all meaning. Reality itself seems to end. Yet physicists hesitate, for infinities are less likely to be features of nature than signs of a theory pushed past its limits. The singularity forces a confrontation with the deepest paradox in modern science, the fate of information. According to quantum mechanics, information about a physical system, its precise state, can never be destroyed. But in a black hole, matter appears to vanish irretrievably, consumed by the event horizon and crushed into nothingness. In the 1970s, Stephen Hawking revealed an unexpected twist. Black holes are not eternal. They emit faint thermal radiation, born from quantum effects near the horizon. Over time, this Hawking radiation would cause a black hole to shrink, evaporate, and eventually disappear. Yet, if the black hole vanishes, and with it the information of everything it consumed, a contradiction arises. The laws of quantum mechanics insist information survives. Relativity appears to suggest otherwise. This information paradox has inspired countless attempts at resolution. Some theories propose that quantum corrections prevent the singularity from ever forming. Instead of a point of infinite density, the core could be replaced by a more complex structure, fuzzball, as string theory imagines, woven from tangled strands of vibrating energy. In this picture, the interior is not empty but filled with a dense, intricate web, preserving the information within. Others suggest that information is somehow imprinted on the event horizon itself, encoded in subtle quantum correlations carried away with the radiation. Black holes have also become recognized as thermodynamic systems, obeying laws that mirror those of heat and entropy. The horizon area functions as entropy, a measure of hidden microstates, while surface gravity behaves like temperature. This discovery links black holes not only to gravity and quantum theory, but also to statistical mechanics, hinting that all three realms might be aspects of a deeper, unified framework. The famous formula inscribed on Hawking's tomb relating entropy to the horizon's surface area remains one of the most profound equations in modern science, binding together fields once thought separate. Mainstream consensus today accepts a humbling truth: the physics we have is incomplete. General relativity captures the grand sweep of spacetime, quantum mechanics the restless dance of particles, but neither alone can reveal what happens at the edge of a singularity. The paradox is that black holes present are not flaws to be dismissed. They are signals, pointing to the next revolution in science. Somewhere beyond the horizon of current theory lies the answer, waiting for a language capable of uniting the vast with the minute, the continuous with the discrete. Black holes, in their silence, remain teachers. They whisper of a cosmos where reality is richer than equations can yet describe, and where the most terrifying void may conceal the architecture of a deeper truth. The concept of a singularity has long stood as the sharpest edge of Einstein's theory. Yet many scientists believe it is not the final word but a placeholder for unknown physics. Singularities reveal where the map of our knowledge ends, but they do not necessarily mark where nature itself must break. This realization has drawn attention to quantum gravity, an elusive framework that would weave relativity and quantum theory into a single fabric. Until such a theory is complete, The singularity remains a boundary of understanding, rather than a definitive feature of the cosmos. Among the most compelling efforts to bridge this gap is the idea that black holes might not be empty voids with unreachable cores, but structured entities with profound internal complexity. The fuzzball concept from string theory embodies this vision. Instead of collapsing into a dimensionless point, matter is believed to stretch into tangled filaments of energy, creating a dense but finite structure. If true, fuzzballs would sidestep the paradox of infinite density while storing information within their very fabric. In this way, information would not vanish, would simply be hidden in forms almost impossible to decode. Another path has emerged from the strange marriage of quantum theory and gravity, the holographic principle. Inspired by black hole entropy, this principle suggests that the three-dimensional interior of a black hole and perhaps all of reality may be described by information encoded on a two-dimensional boundary, just as a hologram projects depth from a flat surface. Spacetime itself could be an emergent illusion born from information spread across a horizon. This radical notion reshapes the paradox. If information is written onto the event horizon, then Hawking radiation might not erase it after all. Instead, the information could be scrambled and radiated outward in a form far beyond human decoding, yet still preserved in principle. Thermodynamics deepens the mystery further. The entropy of a black hole is immense proportional not to its volume, but to the area of its horizon. This fact suggests that space itself may store information in units as tiny as the Planck length, a scale so small it defies intuition. Black holes, therefore, are not just cosmic vacuums but ultimate storage devices, holding more information than any other object of comparable size. In this view, the universe treats horizons as the fundamental ledgers of existence, tallying every particle and every quantum state with exacting precision. Hawking's discovery that black holes radiate like thermal bodies challenged the notion of their eternal silence. Yet the radiation itself remains too faint to measure directly for stellar mass or supermassive black holes, detectable only for hypothetical microscopic ones that may never exist. Still, the mathematics is persuasive, and the paradox endures. If a black hole can evaporate, what remains when the last photon escapes? Does it vanish entirely, leaving no trace of what once fell inside? Or does some remnant survive a shadow of information, preserved in a final whisper of quantum memory? The mainstream view acknowledges the tension without resolution. Relativity sketches the horizon and the collapse. Quantum mechanics insists on the permanence of information, and thermodynamics ties the two together in a system more profound than either field alone can capture. The consensus is not that one picture is correct and the others are false, but that all are fragments of a deeper, unseen whole. Black holes are paradoxical not because they disobey natural law, but because they reveal that our laws are incomplete here. At the intersection of infinities and probabilities, science confronts its greatest humility. The singularity, the fuzzball, the holographic horizon each, is less an answer than a question refracted into new light. Black holes remain what they have always been, nature's ultimate reminder that mystery is not a flaw in our knowledge, but the very engine of discovery. As the mainstream frameworks strain under the weight of paradox, a more daring branch of thought emerges, one that ventures beyond the established borders of physics. Here, on the speculative edge, the imagination of science stretches toward possibilities that blur the line between what is testable and what is merely glimpsed in equations. Black holes, in this frontier, are not just endpoints of stars or guardians of singularities. They become gateways to visions of reality more exotic than the human mind has ever comfortably held. Loop. Quantum gravity offers one of the first bridges into this territory. It proposes that space itself is not continuous, but woven from discrete loops at the Planck scale. If so, then collapse may never reach an infinite point. Instead, the implosion of matter halts at a minimal volume, compressed to the smallest possible quantum granule. At that threshold, gravity may reverse, transforming the black hole's core into a bounce. What appears from the outside as a final abyss may, from the inside, unfold as a rebirth, a transformation of collapse into expansion. Such a bounce hints at the possibility that black holes could open onto new phases of reality, or even new universes, stitched into the greater multiverse. This speculation flows naturally into the more radical idea of white holes. In classical theory, a white hole is the time reverse of a black hole. Instead of swallowing matter, it ejects it. No evidence of such an object has ever been observed, yet mathematics leaves room for their existence. If black holes one day transition into white holes through quantum processes, then what falls in may not be lost, but expelled elsewhere. Perhaps in a distant future, or in another realm of spacetime entirely. Wormholes, too, enter the conversation, mathematical tunnels linking distant regions of the universe, or even different universes altogether. Though such passages would require conditions far beyond any technology humanity could wield. Their presence in solutions to Einstein's equations reminds science that nature itself may harbor roots far stranger than simple voids of destruction. Equally bold is the holographic interpretation of black holes, extended now beyond the mainstream into wild new territory. If the three-dimensional contents of a black hole are written across its two-dimensional horizon, then perhaps all of space-time is fundamentally holographic. Every particle, every force, every instant of time may emerge from deeper informational laws that have no direct analog in the familiar world. In this vision, black holes become not anomalies, but central keys. Laboratories where the holographic code of the cosmos is most fully expressed. From here, speculation takes a leap into philosophy disguised as physics. Some researchers propose that black holes function as computational engines, performing calculations at the ultimate edge of physical law. The simulation hypothesis, in its more provocative form, suggests that if the universe itself is underpinned by information, then black holes could be the processors, the cosmic equivalents of logic gates. Their horizons and radiation become symbols of computation, so powerful that they might simulate entire realities within their depths. To entertain this view is to wonder whether black holes do not merely reside in the universe, but whether the universe itself resides within their mathematics. Others seek to tie these enigmas to the most elusive elements of the cosmos: dark matter and dark energy. Dark matter, invisible yet massive, clings to galaxies and shapes their fates. Dark energy, even stranger, drives the expansion of the universe faster and faster. Some have wondered whether black holes are not just affected by these forces, but linked to them. Could primordial black holes, born in the earliest fractions of a second after the Big Bang, account for dark matter's missing mass? Could the quantum vacuum energy surrounding horizons whisper clues to the accelerating universe? No consensus exists, but these questions deepen the suspicion that black holes are woven into the very skeleton of cosmic evolution. Speculation of this kind hovers delicately between science and philosophy, but it reveals something profound. Black holes are no longer seen merely as cosmic destroyers. They are canvases onto which humanity projects its boldest theories, its deepest anxieties, and its most ambitious hopes. Whether they are bounces or bridges, holograms or engines, seeds or simulations, they remain the places where human thought presses most forcefully against the boundary of the unknown. In these speculative theories, Black holes shift from obstacles to opportunities, from dead ends to gateways. And while evidence may not yet confirm such visions, their very existence in scientific discourse reflects the restlessness of the human mind, its refusal to accept mystery without exploration. For every question black holes close, they seem to open another, each more profound than the last. To follow the thread of speculation deeper is to enter a realm where physics becomes almost indistinguishable from metaphysics. Each proposed model stretches known science until it seems strain, revealing not only the gaps in human understanding, but also the boldness of the human imagination. Black holes, once dismissed as impossible, now stand as fertile ground for theories that dare to redraw the very architecture of existence. Loop quantum gravity's bounce model, for instance, does more than prevent a singularity. It raises the provocative question: if a collapsing star can rebound, then what lies on the other side of that rebound? Some theorists describe the interior of a black hole not as a prison, but as a bridge to an expanding cosmos, one hidden from external view. In this sense, every black hole might be a cosmic womb, its event horizon the veil that conceals the birth of another reality. This possibility reframes collapse itself, turning destruction into creation, death into genesis. Though unproven, the mathematics offers a tantalizing glimpse of a universe that is not a solitary whole, but a branching tree of worlds. The wormhole hypothesis extends this imagery into stranger territory. If wormholes exist, they could serve as shortcuts across spacetime, tunnels through the cosmic fabric that defy the limitations of light and distance. Yet even in speculative models, these structures are unstable. They would collapse instantly unless threaded with exotic matter substances with negative energy density that have never been observed in nature. Some scientists argue that the very presence of black holes hints at conditions extreme enough to sustain such passages, at least for fleeting moments. In that ephemeral instant, a window could open, linking what appeared to be distant, unconnected realms. The holographic principle, too, grows bolder in speculative hands. In its mainstream form, it suggests that information about everything inside a black hole is encoded at its horizon. But in speculative extensions, the entire universe is treated as a hologram, its three-dimensional richness an illusion projected from a deeper, hidden two-dimensional layer. If true, then the interior of a black hole may not exist in the way human intuition imagines. The fall into darkness could be nothing more than the unraveling of an encoded script, the collapse of information into a tapestry woven across the horizon itself. In this view, what humanity calls inside is not a place at all, it is a transformation of information into geometry. Further into the speculative edge lies the idea of computation. If reality is built on information, then black holes could be the most powerful processors in existence. Their horizons, with their nearly infinite capacity for encoding information, might serve as engines for calculating the unfolding of universes. In some daring visions, black holes are likened to cosmic mainframes, silently executing the laws of physics in a way that no laboratory machine could rival. From this thought flows the simulation hypothesis, extended to its extreme. If the cosmos itself is a computation, black holes may be the processors that sustain the simulation. The falling of a star into their depths might not be the annihilation of matter, but the execution of code at the deepest level of reality's architecture. Connections to dark matter and dark energy bring speculation back to the mysteries most pressing in modern cosmology. Some have suggested that primordial black holes, formed in the earliest instance of the Big Bang, could compose the unseen mass that binds galaxies together. If so, then the invisible scaffolding of the universe is not made of unknown particles, but of countless black holes too faint to detect. Others hypothesize that the energy fields around horizons might influence the expansion of space itself, whispering a possible link to the enigmatic force driving galaxies apart at ever-accelerating speeds. Though evidence remains elusive, these ideas reveal how black holes might intertwine with the largest-scale mysteries in the cosmos. And finally, the multiverse hypothesis expands black hole speculation into infinity. If collapse gives way to bounce, then every black hole may ignite a new Big Bang, birthing a universe with its own laws of physics. Some may collapse quickly, unstable and shortly. Others may endure, expanding into vast and intricate structures like the cosmos we know. In this vision, the observable universe is not unique, but one blossom in a cosmic garden without end. Perhaps even the universe known to humanity was born from such a process, its origins hidden not in a singular beginning, but in the collapse of a parent cosmos beyond all memory. In these speculative frameworks, black holes become more than objects of fear or curiosity. They are thresholds, doorways, not just into space, but into imagination, into questions that press against the boundaries of science itself. While no telescope or detector can yet confirm such visions, the act of contemplating them transforms the mystery. What began as an impossible shadow in Einstein's equations has become a crucible for human thought, where destruction and creation, physics and philosophy converge that the truth remains hidden beyond the horizon. Yet each speculative theory, whether it speaks of bounces, wormholes, holograms, or multiverses, underscores a profound reality. Black holes are not merely the most powerful objects in the universe. They are mirrors, reflecting back humanity's own hunger to understand, to reach beyond, to see not only what is, but what could be. Across the quiet of the 21st century, humanity has begun to press its instruments closer to the edges of the abyss. With each advance, the once invisible now trembles on the brink of sight, and the most powerful objects in the universe yield traces of their secrets, if not yet their innermost core. Black holes, once shadows in mathematics and whispers in starlight, have become targets of direct investigation, their presence probed by machines that orbit Earth and observatories that spread across continents. The rise of next-generation telescopes has given vision to what was once unseeable. The Event Horizon Telescope, a network spanning the globe, offered humanity its first glimpse of a black hole's shadower, dark void framed by a halo of light torn apart by gravity's hand. Yet this achievement was not an end, but a beginning. New observatories, such as the James Webb Space Telescope, now turn their mirrors toward galactic centers, tracing the faint signals of matter spiraling toward horizons that no light escapes. Future missions promise sharper eyes still, space-based interferometers that may one day resolve the turbulence of matter at the very threshold of oblivion. But light is not the only messenger. With the detection of gravitational waves, space-time itself became a medium of knowledge. LIGO and Virgo recorded the tremors of black holes colliding, vibrations in the very fabric of reality echoing across billions of years. Each detection carried within it a story masses measured, spins inferred, distances mapped. With every signal, astronomers now catalogue the secret lives of these objects, their courtships, their spirals, their catastrophic mergers. And as new detectors prepare to come online, Kagra in Japan, the planned LISA mission in space, the orchestra of the cosmos, will be heard in greater clarity. Entire symphonies of gravitational music wait, promising insight into collisions too distant or faint for current instruments to catch. Meanwhile, the invisible processes around black holes are recreated in the domain of simulation. Supercomputers model the torrents of plasma in accretion disks, where magnetic fields twist into titanic jets that span thousands of light-years. These digital laboratories render what no eye can see: the chaos of matter heated to millions of degrees, the rhythm of particles as they spiral toward horizons. Each simulation becomes an experiment, guided by physics yet reaching into regimes no terrestrial experiment could achieve. In this way, humanity gains shadows of insight into the mechanisms that make black holes, not merely destroyers but also engines shaping the galaxies around them. At the edge of computation, quantum technologies promise something more. Traditional machines strain under the weight of simulating gravity's union with quantum mechanics, but quantum computers may open pathways into this frontier. Their ability to manipulate entanglement and superposition could offer models of black hole thermodynamics, perhaps even test frameworks that unify relativity with the quantum realm. Though still in their infancy, these machines mirror the very puzzles they are meant to study, embodying principles that black holes themselves seem to encode at cosmic scales. And above all stands the ambition of future missions. NASA's Laser Interferometer Space Antenna, scheduled to launch in the coming decades, will listen to the deepest rumbles of spacetime, capable of detecting supermassive black hole mergers that ground-based observatories cannot hear. Other concepts, still in their infancy, imagine arrays of satellites that could image horizons with unparalleled precision, or instruments sensitive enough to capture the faint polarization of light twisting near the edge of eternity. Yet despite this progress, the central mystery remains untouched. Every telescope, every detector, every simulation halts at the same boundary, the event horizon. What lies beyond still belongs to speculation, a theater where physics falters and imagination must fill the void. Humanity has surrounded the black hole with instruments and equations, but its interior remains a silence that no signal crosses, a place where theory speaks louder than observation. For now, black holes remain paradoxical monuments, studied in detail, yet unknowable at their heart. The pursuit continues, driven not only by science, but by a deeper compulsion, the need to see into the unseeable, to know what becomes of matter, energy, and time itself when pressed against the limits of reality. In these efforts, the line between knowledge and wonder grows thin, and humanity approaches, step by cautious step, the horizon of ultimate truth, aware that even with all its tools, the interior remains hidden, a secret sealed in darkness. Ion, the need to pierce the veil of cosmic ignorance. Every discovery sharpens the outline of the unknown, as though nature permits humanity to sketch the shape of the puzzle, but forbids the sight of its solution. Ambitious projects rise to meet this challenge. In Europe, the proposed Einstein telescope and the US-based Cosmic Explorer promise to listen with sensitivity far beyond current detectors. Their colossal underground chambers will trace gravitational waves not just from cataclysmic black hole collisions, but from the faint whispers of the early universe. If realized, these observatories may allow scientists to hear the aftershocks of events that occurred before galaxies even formed, pushing black hole research into the realm of cosmological origins in orbit. Engineers dream of X-ray interferometers, vast fleets of spacecraft working in perfect coordination, designed to capture high-energy radiation emitted as matter spirals toward destruction. Unlike optical telescopes, these instruments could see the most violent processes in exquisite detail, the last milliseconds of falling stars, the chaotic dynamics of matter twisting around horizons. With X-rays as their palette, humanity could paint portraits of black holes in a spectrum, where their true ferocity is laid bare. Equally vital is the pursuit of precision timing. Pulsar timing arrays, using networks of radio telescopes across the world, measure the faint rhythmic flashes of neutron stars as though they were cosmic metronomes. Variations in their ticking may reveal low frequency gravitational waves from supermassive black hole binaries too vast for other instruments to capture. These efforts extend human perception into a frequency band where the cosmos hums with the slow, deep tones of colossal black hole pairings, signals that may take years, even decades, to resolve. Meanwhile, particle physicists and astrophysicists converge on the question of information. Can the mysteries of black holes be tested indirectly by studying how quantum fields behave under extreme conditions? Laboratory analogues, such as black hole mimickers in Einstein, condensates seek to recreate the mathematics of horizons in miniature. Though these tabletop experiments cannot duplicate a singularity, they provide windows into phenomena like Hawking radiation, offering possible glimpses of the principles that govern the cosmos at its limits, even beyond Earth. Black hole exploration is becoming an international endeavor. China's proposed space-based gravitational wave observatories, India's expansion into high-energy astrophysics, and multinational collaborations on deep space telescopes all point to a future where no single nation holds the key. Humanity as a species is gathering around the question, pooling ingenuity and resources in pursuit of an answer that transcends borders. And yet, all these grand projects circle the same impassable frontier. The horizon remains silent, reflecting no message, guarding the enigma of what lies within. This tension, the ability to probe almost every layer of the black hole but not its core, is both a frustration and a gift. It ensures that the mystery remains alive, that science continues not as a completed story but as an unfolding narrative, as suspenseful and unfinished as the cosmos itself. What makes this pursuit remarkable is not simply the technology, but the philosophical undertone it carries. Each instrument is a question cast into the dark. Each detection, whether of light, waves, or particles, is an answer whispered back across unfathomable distances. And each whisper points to a paradox. The closer humanity comes to black holes, the further away their innermost truths recede, as if the universe insists that some knowledge must be earned only in fragments. Thus the quest endures. The next generation of telescopes and detectors will not resolve the mystery outright, but they will deepen it, enriching the human story of pursuit. Every image, every signal, every simulation will be another brushstroke in a portrait of the abyssal portrait that, though unfinished, reveals the elegance of the attempt. For black holes are not merely scientific challenges. They are mirrors in which humanity confronts its own hunger to know, to see, to understand what lies beyond the veil of comprehension. In this confrontation, science becomes poetry, and the darkness itself becomes a partner in dialogue. Humanity presses onward, guided by both instruments and wonder, reaching always toward the horizon, aware that the final secret still sleeps in silence. Across cultures and centuries, the black hole has become more than an object of physics. It is a symbol, a cosmic riddle that reflects the deepest anxieties of the human condition. To confront a black hole is to confront annihilation itself, where matter, time, and memory vanish into an abyss with no promise of return. For many, it is not only the most dangerous object in the universe, but also the purest embodiment of the unknown. Within its silence, humanity projects its fears, the fear of death, of endings, of an edge to existence where meaning dissolves. And yet, paradoxically, the same object embodies creation. The collisions of black holes sculpt gravitational waves that ripple through the universe, carrying energy across billions of years. Their violent jets ignite galaxies, stirring the raw material of stars. In destruction lies creation, and in endings lie beginnings. This paradox is not only physical, it is philosophical. For thousands of years, human beings have looked at the night sky with awe and terror. Ancient stargazers mapped constellations as stories of gods and beasts. Philosophers saw the heavens as an eternal order beyond reach. Centuries later, Einstein bent this order, showing that gravity is not a force but a curvature of space and time. Hawking, in turn, revealed that black holes might not be eternal, that even the darkest abyss leaks energy in a slow whisper of radiation. Each generation inherits the mystery and reshapes it, layering insight upon wonder. Yet black holes resist finality. They act as metaphors for boundaries that humanity cannot yet cross, the boundary of life, the edge of time, the limit of understanding itself. To study them is to face humility, to recognize that even in an age of satellites and supercomputers, there are truths that remain beyond reach. Perhaps this is their greatest lesson, that knowledge is not a possession, but a pursuit. The human spirit, however, does not surrender. It leans into the abyss with curiosity that eclipses fear. In the silhouette of the event horizon, it does not only see darkness, but a mirror. The black hole reflects the drive to explore, to push against limits, to transform ignorance into discovery. It reveals that mystery is not an obstacle, but a compass, guiding inquiry toward ever deeper questions. And so, the final reflection emerges. What lies inside the most powerful object in the universe may never be seen, never be measured, never be brought fully into the light. But perhaps this absence is itself the answer. The black hole does not hand humanity closure, it hands it a question, the ultimate frontier of existence. In its shadow, science and philosophy converge, and the human story continues, drawn ever forward by the silent pull of the unknown. In this confrontation, science becomes philosophy in motion. The black hole ceases to be only an object of equations and transforms into a mirror held against the human spirit. Its silence speaks to the limits of ambition. Its mystery echoes the boundaries of comprehension. To gaze into it is to feel the weight of one's own impermanence. A reminder that life itself is fleeting when measured against the ages of the cosmos. And yet, within this fleetingness lies meaning. Black holes remind humanity that fragility is not weakness, but the condition that makes wonder possible. If existence were eternal and answers were easy, curiosity would wither. It is precisely because time runs out, because mysteries resist resolution, that the pursuit gains its intensity. The darkness at the heart of galaxies teaches that limits are not walls, but horizons' edges that call explorers closer. Philosophers have long spoken of death as the ultimate unknowable, the veil that no voice returns from. In many ways, the black hole is a cosmic metaphor for this same veil. It embodies the passage into what cannot be described, where even language and mathematics falter. Yet just as individuals continue their lives knowing death awaits, so does humanity press forward, knowing that the singularity may forever lie beyond sight. The courage is not in reaching it, but in daring to approach. Across history, every era has found its reflection in the heavens. The Greeks saw gods in the constellations. Medieval thinkers saw divine order. Modern science sees equations woven into spacetime. Today, black holes hold the place of ultimate mystery, shaping both scientific ambition and existential reflection. They are not just destinations of collapsing stars, but symbols of the human struggle with the infinite. Even religion and philosophy, though varied in form, often echo the same themes. The abyss can be a stand-in for the unknown realms of spirit, for the boundary between the seen and the unseen. In this sense, black holes unite science and spirituality, not by providing answers, but by embodying the eternal question of what lies beyond. Perhaps, then, their true gift is humility. For all its progress, humanity remains a young species, barely able to listen to the faintest signals of the cosmos. The universe does not yield its deepest truths easily, and maybe it should not. Perhaps mystery itself is the engine that propels discovery, the silence that forces the mind to ask, to reach, to imagine. The black hole, the most powerful object in existence, does not roar or blaze. It whispers in absence, in gravity, in the bending of time. It asks nothing, yet it compels everything. And in its presence, humanity sees both its fragility and its resilience, an animal of dust, daring to measure infinity. The chapter closes not with certainty, but with reflection. Inside the black hole may never be revealed, yet in pursuing it, humans uncover something else, an understanding, not of what lies within the abyss, but of what lies within themselves. The unyielding hunger to know, the courage to ask, and the wonder that endures even when answers remain out of reach. The silence of a black hole is not emptiness, but a profound fullness. It is the silence of a question so vast that it cannot yet be spoken, a silence that invites reflection rather than resolution. The event horizon marks a physical boundary, yet it also functions as a metaphorical threshold, the edge where comprehension falters and imagination takes its first steps into the unknown. Humanity stands at that threshold, armed with telescopes, equations, and dreams, but also with fears, doubts, and the awareness of mortality. Black holes are cosmic riddles, but they are also mirrors. They reflect the human struggle to reconcile opposing truths, fragility against resilience, ignorance against insight, transience against eternity. To contemplate them is to confront the paradox of existence itself, that living beings of finite duration can even ask questions about infinity. In their darkness lies a reminder that the universe is not built for human comprehension. Yet somehow, human comprehension persists, straining against the veil of the unknown. The notion of annihilation resonates deeply in the human psyche. From the earliest myths of underworlds and apocalyptic visions to the philosophical meditations on death and nothingness, cultures have sought metaphors for the absolute end. Black holes embody this concept in nature itself. They are stars that have died so violently they erase not only their own form but the very fabric of space around them. They consume matter, energy, even the information that defines reality. And yet, within this destructive force lies the possibility of creation. The jets launched from their accretion disks seed galaxies with energy, influencing the growth of stars and shaping cosmic architecture. In destruction, there is sculpting. In silence, there is a voice. This paradox, destruction as creation, mirrors humanity's own existence. Every generation is shaped by what has ended before it. Every discovery built on the ruins of discarded theories. Civilizations rise and fall, yet their ashes become the soil for what follows. In this sense, black holes are not alien to human experience. They are cosmic reflections of cycles humanity has always known, only scaled to infinity. Einstein's equations first hinted at their existence, but the man himself doubted such objects could manifest in reality. They seemed too extreme, too final, too paradoxical to inhabit the same universe as galaxies and planets. Yet they proved real, and their reality continues to challenge assumptions about what is possible. Just as Einstein's contemporaries had to expand their understanding, so must this generation confront the possibility that black holes hold secrets that redefine not only physics but the very nature of reality. The singularity, a point where density becomes infinite, may not exist in the literal sense, but as a symbol it represents the collapse of knowledge. At the heart of every black hole lies not just matter compressed, but human understanding crushed to its limit. Equations diverge, logic stumbles, and certainty vanishes. What remains is not a conclusion, but a question. And perhaps the deeper truth is that questions, not answers, are the true measure of progress. The information paradox deepens this reflection. If information vanishes within black holes, the laws of physics fracture, undoing the principle that the universe is a coherent whole. But if information survives, transformed in ways not yet understood, then reality itself may be stranger and more resilient than imagined. Hawking, in wrestling with this dilemma, became not only a scientist but a philosopher, reminding the world that physics is not immune to existential tension. His admission that he might have been wrong was not weakness, but courage, the kind of humility that the cosmos demands. And so, black holes are not only objects of study, but teachers. They teach humility, reminding humanity of its limits. They teach wonder, showing that even the most terrifying void can inspire beauty. They teach persistence, for their riddles are not solved in one lifetime, but through the patience of generations. Each discovery, radio emissions, X-ray binaries, gravitational waves, shadows captured by telescopes, is a fragment of a larger mosaic still incomplete. The pursuit itself becomes a metaphor. Progress is not about completion, but continuation. This is perhaps the most profound philosophical lesson of all. To live, knowing death awaits, is to mirror the scientific pursuit of black holes. Both are acts of defiance against inevitability. The individual cannot escape mortality, just as scientists may never fully escape ignorance. Yet both continue, not because the end can be conquered, but because the journey itself has meaning. The human fascination with horizons runs deep. Horizons are both barriers and invitations, limits that both constrain and beckon. The horizon of Earth's oceans once marked the end of the known world, yet sailors ventured beyond it. The horizon of the atmosphere once marked the end of human flight, yet rockets transcended it. Now, the cosmic horizon, the event horizon, marks the edge of physics as currently understood. It, too, invites a journey. Perhaps humanity will never cross it, but the act of striving is itself transformative. In art and literature, black holes have taken on symbolic weight. They are metaphors for depression, for obsession, for loss, for the inescapable pull of grief or memory. They appear in poetry as symbols of longing, in novels as symbols of fear, in films as symbols of awe. This cultural resonance reveals that they are more than astrophysical entities, they are psychological archetypes. They give shape to the intangible, offering an image of what it means to be drawn toward, something that both terrifies and fascinates. From another perspective, black holes embody the paradox of time. At their horizon, time slows to a crawl relative to the outside world. For the falling traveler, moments pass normally, yet for the distant observer, the traveler freezes, suspended at the edge forever. This duality of perception becomes a meditation on life itself. Time feels ordinary from within, but appears fleeting from without. To reflect on a black hole is to reflect on one's own perception of time, the days that feel endless, the years that vanish in memory, and beyond this meditation lies an even deeper mystery. If black holes are laboratories of quantum gravity, then to study them is to study the architecture of existence. They might hold the key to unifying the cosmic with the microscopic, the infinite with the finite. And yet, even if they never yield this key, they still perform their role as teachers. They remind humanity that some doors may never open, and that wisdom lies as much in recognizing limits as in breaking them. The question then arises, what is humanity truly seeking? To peer inside a black hole is not only to learn about physics, but to confront desire itself. Is the pursuit of knowledge an attempt to escape mortality? Is it a way to leave a mark on eternity? Or is it simply the expression of curiosity, a trait so deeply ingrained that it transcends survival. Perhaps the truth is that the answer does not matter. The asking itself is enough. In the long future, black holes will outlast stars, planets, and perhaps even galaxies. They will endure when the night sky grows dark, when fusion has ceased, when the universe becomes sparse and cold. They are the keepers of time on scales beyond human imagination. To study them now, in this brief moment when the cosmos is still vibrant, is to write humanity's name in the ledger of eternity, however faintly. The fact that fragile beings of dust and water can even imagine such things is itself extraordinary. The ultimate reflection is this: black holes may never reveal their interiors. Their secrets may remain sealed behind horizons that no light escapes. But the pursuit of those secrets has already transformed humanity. It has reshaped physics, inspired philosophy, and deepened cultural imagination. It has humbled and elevated in equal measure. Perhaps what lies inside the most powerful object in the universe is not a singularity or a paradox, but a reflection of humanity's own drive to seek, to question, to wonder. And so the story comes full circle. Black holes began as mathematical curiosities, then emerged as astrophysical realities, and finally became symbols of the human condition. They are reminders that the unknown is not an enemy but a companion, guiding thought toward horizons both cosmic and personal. The abyss may never be crossed, but it continues to call, and in answering that call, humanity discovers not the heart of the black hole, but the depth of its own spirit. Perhaps, then, the greatest truth is that the universe's most dangerous object is also its greatest gift. It is the eternal question, silent, unyielding, infinite. A question that does not diminish life, but enriches it. For in seeking the unknowable, humanity learns to cherish the knowable, the fleeting moments under the stars, the fragile warmth of light, the miracle of being able to ask at all. The journey into the black hole is not a voyage of spacecraft or instruments, but of thought, imagination, and humility. No machine can pass through the horizon and return. No probe can transmit signals from within. And so, the mind itself becomes the explorer, shaping questions into vessels that attempt to cross the boundary. This is where philosophy and physics converge, where equations are haunted by silence, and silence itself becomes a kind of knowledge. Humanity has always sought mirrors for its own condition, and the black hole provides one unlike any other. The ancients looked at eclipses and imagined divine punishment. They saw comets and believed they heralded doom. But the black hole is a mirror of a higher order, a cosmic truth that human eyes cannot see but human minds cannot ignore. It embodies the fear of obliteration, yet also the dream of transcendence. To fall into one is to lose all distinction, to dissolve into an unreturning silence. And yet, paradoxically, it is within these same regions that the laws of physics might bend toward unimagined futures. In the 21st century, humanity lives in an age of both wonder and fragility. Technologies have revealed distant galaxies, mapped the cosmic microwave background, and confirmed gravitational waves rippling through the universe. Yet those same technologies reveal the smallness of human existence. Against a backdrop of billions of galaxies, human lifespans are whispers. Against the pull of a singularity, human power is nothing. And still, the curiosity persists. It is this persistence that makes the human spirit echo cosmic processes themselves, continually collapsing old certainties, continually igniting new stars of thought. The fear of black holes is inseparable from the fear of death. Both represent a finality beyond comprehension, an erasure of individuality and memory. The singularity can be seen as a metaphor for that final compression of experience, the point where all stories converge and vanish. Yet just as scientists ask whether information is truly destroyed within black holes, so to do humans wonder whether something of consciousness endures beyond death. Here, science cannot yet answer, but the parallel between the cosmic and the personal gives resonance to the pursuit. Every equation probing the fate of particles near an event horizon echoes humanity's quiet hope that meaning is never lost. Einstein once called the concept of singularities abominable. Eddington declared collapse into nothingness absurd. There, rejection was not only scientific but emotional, an instinctive recoil from the thought of infinity in the heart of nature. But history has shown that what is first resisted often becomes the very path of discovery. Chandrasekhar, who endured scorn for his prediction of stellar collapse, was vindicated decades later. Hawking, who dared to propose evaporation, turned terror into possibility. Each generation faces the same choice: to turn away from the abyss, or to let its gravity draw thought closer. In the cultural imagination, black holes are symbols of obsession. They appear in films as gateways, in literature as metaphors for grief or madness, in music as motifs of despair or transcendence. They embody the sense of being pulled toward something inescapable, whether it is love, ambition, or sorrow. This universality explains why they grip not only scientists but artists, poets, and philosophers. The black hole is not just astrophysical. It is archetypal, a Jungian shadow cast across the cosmos itself. The paradox of time within their grasp adds further depth. To an observer far away, matter falling into a black hole appears to freeze at the horizon, time stretched toward eternity. To the infalling traveler, time proceeds normally, with no sense of crossing a boundary. This duality is not merely a puzzle of relativity, it is a reflection of human experience. From the outside, another's life may seem to pass in a blink, while from within, moments feel infinite. Memory itself becomes a kind of horizon, events receding into still frames, frozen yet unreachable. Such reflections lead to the recognition that black holes are not only objects of destruction, but of perspective. They remind humanity that reality is layered, that what seems absolute in one frame may dissolve in another. This insight extends beyond physics into ethics, culture, and self-understanding. The recognition that truth may depend on vantage point is both unsettling and liberating. It destabilizes certainty, but enriches empathy. The future of black hole research will not only clarify the structure of space and time, but will also continue reshaping the human self. For centuries, humanity placed itself at the center first of Earth, then of the solar system, then of the galaxy. Each discovery moved that center outward, revealing insignificance. But black holes reverse the narrative. They show that even in a universe vast beyond measure, points of infinite depth exist. They teach that meaning does not only come from scale or position, but from intensity. In that sense, they provide a strange comfort, reminders that smallness does not preclude significance, and that mystery itself gives weight to existence. There is also the matter of ultimate fate. Black holes are not eternal. Hawking radiation predicts their slow evaporation over unimaginable spans of time. Long after stars fade, galaxies dissolve, and matter decays, black holes will whisper their last photons into the darkness. In that distant epoch, when the universe is old beyond comprehension, they will vanish, leaving only silence. What, then, will remain? Perhaps nothing but space, cold and empty. Or perhaps something still unknown, a residue of laws not yet uncovered. To imagine this is to confront the possibility that the universe itself may be finite in expression, even if infinite in scale. And yet, paradoxically, these distant endings do not diminish the present. they enhance it. To know that black holes will one day vanish is to recognize the fragility of all existence. Fragility, however, is not weakness, it is the source of value. A flower that blooms forever has no urgency. A star that never fades offers no wonder. It is in the finitude, the passing, the transience, that beauty arises. Black holes, in their silent inevitability, remind humanity of this truth, that the moment matters because it will not return from another angle. Black holes remind humanity of the power of collective thought. No individual could capture their image, no single mind could prove their properties. It required thousands of scientists, engineers, philosophers, and dreamers across centuries, building instruments that span continents and theories that span disciplines. This collaboration is itself a triumph. Against the vastness of space, the human species has found a way to work as a whole, pooling minds to glimpse the unseen. The shadow of M87*, the vibrations of colliding horizons, the simulations of accretion disks, these are not the work of one, but of many. And in this, black holes reveal not only the nature of the universe, but the nature of humanity, fragile alone, powerful together. In contemplating black holes, humanity discovers itself. It discovers its limits, yes, but also its aspirations. It discovers that even in the face of mystery that may never yield, the act of asking remains noble. Perhaps the black hole is not a doorway to another universe, but a mirror of this one, reflecting the endless hunger of beings who refuse to stop seeking. Perhaps, ultimately, the black hole does not guard an answer at all. Perhaps it is the answer, the embodiment of the truth, that reality is infinite in questions, finite in understanding, and beautiful in the tension between them. And so the reflection deepens. The black hole becomes not just a scientific object, not just a philosophical metaphor, but a spiritual horizon. It asks each mind, what lies beyond your own event horizon, the boundary of what you can see, know, or endure. To cross that boundary may be impossible, but to imagine crossing it, that is where growth lies. The abyss does not consume only, it teaches. It teaches that ignorance is not shameful, that limits are not failures, that wonder is not weakness. In the end, the most powerful object in the cosmos may hold no secret other than this, that life, however brief, however small, is enriched by the act of turning toward the unknown rather than away from it. To live under the shadow of black holes is to live under the shadow of infinity, and to still choose curiosity, courage, and wonder. That choice is the true victory, the true reflection, the true gift. Thus, the chapter closes not with certainty, but with reverence. Black holes remain questions, and questions remain treasures. They are cosmic reminders that the human journey is not toward the end of knowledge, but toward its endless unfolding. And as long as there are horizons, there will be seekers. As long as there is darkness, there will be those who look into it, not with despair, but with awe. And in that awe lies the quiet realization that the universe itself is not simply to be solved, but to be experienced, reflected upon, and cherished in the endless silence of the cosmos. The dialogue between humanity and the black hole continues. It is a dialogue without words, carried not by sound but by imagination, mathematics, and awe. Each equation written on a chalkboard, each photon captured by a telescope, each simulation run on a supercomputer are fragments of humanity's side of the conversation. The black hole answers only with silence, yet in that silence lies the weight of truths deeper than language can hold. As the centuries pass, black holes may become not merely objects of study but cornerstones of human destiny. The possibility of harnessing their energy, however distant, flickers as a dream in the minds of physicists. The accretion disks that swirl around them release torrents of power, more luminous than galaxies. If such forces could ever be tamed, they would surpass any star, any fusion, any known resource. To imagine civilizations thriving near such engines is to glimpse futures where survival no longer depends on fragile planets but on the gravity wells of collapsed suns. This vision may never be realized, yet the act of envisioning it pushes the frontier of human ambition outward. Yet alongside dreams of utility lies humility. Black holes resist possession. They are not like stars, which can be mapped and measured, nor planets, which can be visited. They are thresholds, edges, abysses. To approach them is to approach a limit not of distance, but of understanding. No matter how refined instruments become, no matter how advanced mathematics grows, there will always remain the unseen interior, hidden beyond the horizon. And it is precisely this inaccessibility that makes them sacred in a scientific sense. Reminders that the universe still holds secrets no hand can touch. The cultural reverberations of black holes will likely outlast even current scientific paradigms. Just as myths of the underworld shaped ancient societies, the concept of horizons beyond return may shape future philosophies and art. Painters may depict the glowing rims of light. Musicians may compose symphonies inspired by the tension between silence and collapse. Writers may weave metaphors of falling and freezing. Each medium will translate the incomprehensible into human terms, just as ancient myths translated eclipses into stories of gods devouring suns. Black holes are the modern sublime objects, so vast, so incomprehensible, that they shatter normal categories of thought. In contemplating them, humans are forced to confront paradoxes. A black hole is both an end and a beginning, both absence and presence. It is the heaviest object in the universe, yet defined by emptiness. It erases everything within, yet shapes everything around. It bends space and time, yet is itself timeless and spaceless in the singularity. These contradictions are not flaws, but lessons, that reality is not obliged to fit neatly into human categories. The universe is not built for comfort. It is built for truth. The question of what lies beyond a black hole's horizon will continue to stir imagination. Some physicists propose wormholes, gateways to other universes. Others envision holographic descriptions, where the three-dimensional world within is encoded on the two-dimensional surface of the horizon itself. Still others suspect that new physics string theory, quantum gravity, or ideas yet unborn will resolve the paradox. But even if answers come, new questions will sprout in their place. The horizon will simply move outward, like a mirage in the desert of thought. This is the pattern of human progress. Each discovery is not a conclusion, but a threshold. Copernicus displaced Earth from the center. Newton explained the motions of the heavens. Einstein revealed the relativity of space and time. Each step widened the horizon, and with each widening came both wonder and disquiet. Black holes are the next such threshold, demanding not only new science but new metaphors for existence. They insist that humans recognize both their insignificance and their potential, insignificant in scale, yet capable of grasping truths written into the structure of reality itself. The encounter with black holes is also a test of patience. Unlike phenomena that can be experimented upon in laboratories, black holes yield their secrets slowly. Decades may pass between breakthroughs, and progress often comes not from direct observation, but from the patient weaving of mathematics and imagination. To study them is to learn endurance, to accept that the universe does not rush to reveal itself. This patience mirrors the slow processes of cosmic time itself, stars burning for billions of years, galaxies colliding over eons, black holes evaporating only after trillions. In aligning thought with these timescales, humanity learns to see itself anew not as masters of the universe, but as participants in its vast unfolding. The philosophical weight of black holes extends to ethics. If reality contains horizons that no one can cross, then perhaps humility should shape human choices as much as ambition. If some mysteries are permanent, then perhaps wisdom lies not only in discovery but in reverence. To stand before the unknown, not as conquerors but as caretakers of curiosity, is itself a moral stance. The universe may not care for human values, but humans, in confronting the universe, may learn to care more deeply for one another. The silence of the black hole becomes a call to listen to each other, to the fragile world, to the brief gift of consciousness. Speculation about the ultimate role of black holes in the fate of the cosmos deepens this ethical reflection. In some cosmological models, they may one day dominate all that remains, their evaporation marking the final whisper of a dying universe. In others, their dynamics may trigger new beginnings, seeding fresh universes beyond the reach of current perception. Whether endings or beginnings, they remind humanity that it is part of a story larger than itself, a narrative written not in centuries but in infinities. To know this is to hold both humility and dignity in balance, humble in the face of scale, dignified in the act of knowing. And yet, even with all the grandeur, the human response remains personal. To imagine falling into a black hole is to imagine the loss of self, the collapse of memory, the end of individuality. This thought, terrifying though it may be, also provides clarity. It sharpens awareness of the present, of the fragile moments that make a life. Just as light near a horizon is stretched and reddened, so too does reflection on death stretch and deepen the value of living. Black holes, though far away, cast shadows into the human heart, shaping meaning as surely as they shape galaxies. As technology advances, humanity may not only observe black holes, but begin to map their neighborhoods in exquisite detail. Simulations may show the dance of magnetic fields and plasma with clarity rivaling art. Interferometers may detect subtler ripples in spacetime, tracing mergers across the universe. New generations may grow up with images of black holes as familiar as pictures of planets are today. And with each new image, awe will deepen, for the closer humanity looks, the more it will see the strangeness that lies beneath the familiar. Yet one truth will remain constant. Black holes are not destinations, but reminders. They remind us that the universe is not exhausted by human thought. They remind us that even in an age of data and machines, mystery endures. They remind that the act of seeking is itself the reward. That answers are not possessions, but invitations to further questions. They remind us that life, fleeting though it is, has the capacity to touch infinity not by crossing it, but by imagining it. Thus, the chapter bends toward its next horizon. Humanity, gazing into the void, discovers not emptiness, but reflection. The black hole is not simply there, in the distant galaxy or collapsing star. It is also here, in the structure of thought, in the rhythm of questions, in the hunger that refuses to fade. It is not only an object of science, but a metaphor of the human condition. And so, the silence continues. Not a silence of absence, but of presence too deep for sound. A silence that invites listening, imagining, reaching. In that silence lies the possibility of endless growth. For as long as black holes exist and as long as minds turn toward them, the story will not end. The horizon will move outward, the questions will multiply, and humanity, fragile yet unyielding, will continue to walk the narrow path between ignorance and wonder, carrying the light of curiosity into the vastness of night, The chapter stretches forward, like time itself drawn into a gravity well, pulled toward a singularity it cannot yet reach. The narrative of humanity and black holes is not complete. It may never be, but in its incompleteness lies its beauty. For it is not the arrival at answers that defines a species, is the courage to ask, to seek, to imagine, and to dream.